In this lecture, we're going to focus on trees. We will formally define what is a tree. We'll look at some properties of trees and see some classical examples of trees. Now that we have seen what it means to be connected and what it means to have a cycle, we can define a tree. The formal definition of a tree is a connected graph with no cycles. We'll use this tree that we've used many times before to talk about these two properties of trees. So, for example, let's discuss connected. Suppose that we were to remove an edge from the graph below. It doesn't matter which edge, but suppose we were to remove the edge C. Then we would not be able to reach the vertex 4 from 1, 2, or 3. So removing the edge C disconnects the graph. Suppose we remove the edge D, then we could not reach the vertex 5. So it doesn't matter which edge we choose to remove, the resulting graph would no longer be connected. That means that a tree has the fewest possible edges for a graph to have and still be connected, because the removal of just one edge will disconnect it. Now, the other property. We've also said a tree has no cycles. So we've seen if you remove a single edge, it's no longer connected. What happens with cycles? Suppose we add an edge. If we pick two vertices that are not connected and we connect them with an edge, what happens to the resulting graph? If we were, for example, to put the edge 2, 4 in, then we generate a cycle. We can go from 1 to 2 to 4 and back to 1. If we were to put the edge 3, 5 in, again, we would generate a cycle. We can go from 3 to 2 to 1 to 4 to 5 and back to 3 if we put the edge 3, 5 in. So we could observe with this graph that trees also have the property that if you add an edge, it doesn't matter which edge you add, you generate a cycle. So trees have this unique property. It's like they're on the border. If you remove a single edge, it's no longer connected. If you add a single edge, you now have a cycle. But a tree is a connected graph with no cycles. So this is a prevalent theme in combinatorics or combinatorial optimization. In general, you want to see how far you can push one property without losing another property. So in this case, how many edges can you remove before you disconnect the graph? Or how many edges can you add before you start generating cycles? And so in this sense, trees are optimal because the answer is just one. Trees have many, many interesting applications. In math, we'll see that a tree is the underlying structure of all connected graphs. In computer science, many, many algorithms are based on a tree traversal. And in chemistry, many of the molecular structures that we will see are in fact trees. Systems biology, for example, use networks as models, but networks are essentially a graph. let's consider an application from chemistry. A molecule that satisfies the chemical formula C sub m H sub 2m plus 2 is called a saturated hydrocarbon. This means for a fixed m, you have m carbon atoms, and you have twice m plus 2 hydrogen atoms. In the trees up above, in this application, the carbon atoms are the vertices of degree 4, and the hydrogen are of degree 1. So how many carbon atoms do we have? We have 5 vertices of degree 4 in both graphs. So we have 5 carbon atoms, and we have 2 times 5 plus 2, or 12 hydrogen atoms. Now, you might notice that these are 2 different trees, or 2 different configurations. So the question was, how many different for a fixed m? So you know how many carbon atoms you want. How many different molecules are possible? Or how many different saturated hydrocarbons could occur in nature? This was unknown until it was answered by John Sylvester. And he wrote a paper where he counted the number of trees that have vertices of degree 4 and degree 1 that satisfy the formula. And in fact, in his paper, he referred to his drawings of molecules as graphs of molecules, and the name stuck. And so that is why we call these things graphs. So back to trees again. Here is a graph that we can call a grid graph. And the blue edges represent an underlying tree structure. Do you agree the blue edges induce a tree? If you remove a single blue edge, you disconnect the blue graph. And if you add a single blue edge, you generate a cycle. So by definition, the structure induced by the blue edges is a tree. So in this lecture, we talked about the formal definition of a tree, a connected graph with no cycles. We looked at some properties of trees, such as if you add a single edge, you generate a cycle, and if you remove a single edge, you disconnect the graph. And we talked about a few classical examples of trees.